Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Yield Line Analysis, and it is going to provide you a broad overview of yield line theory, and also the calculations of this method. I am going to give you an overview of what I am covering in today's video. First of all, we will have a look at some fundamentals of the yield line analysis, then move on to the example of rectangular fixed edge slab, then wrap up with conclusions. The plastic theory is usually rather difficult to apply to reinforced concrete structures because of the limited plastic rotation capacity of concrete sections in bending. However, concrete slabs are almost always very under-reinforced. It is unusual to have sections with more than 1% of reinforcement. Consequently, slabs have considerable plastic rotation capacity and can be successfully analyzed or designed by plastic methods. This video will present the yield line method, which is now widely used. Yield line theory is similar with the method of finding the collapse loads of steel structures. Figure A shows a square slab with reinforcement parallel to the size of the plate. The edges were supported to prevent vertical movement, but offered minimal resistance to rotation, called simply supported edges. On the tension side of the slab, the underside of a floor slab, but called the top in the figure because the test rig applies an upward load to the slab. There are many cracks, especially near the center of the slab. This web of cracks forms at a relatively low load, but as the load increases, only a few of the cracks become large. In this case, the cracks roughly on the diagonals have opened out. On the other compression face of the slab, the concrete has crushed, where the large cracks have opened up on the tension face. This experimental behavior leads to a relatively simple model of the collapse of the slab. The collapse mechanism consists of two yield lines running the full length of the diagonals with rigid triangles, called generally rigid regions, of slab between the yield lines, as shown in Figure B. Figure C shows a model slab with clamped edges, providing complete restraint of the edges against the deformation, after it was tested with an ultimate dead load. The loaded part of the slab was the same size as the simply supported slab. It was necessary to make the spaceman larger, with two lines of bolt holes along each side, to create the clamped edges. The clamped edges slab is the slab equivalent of the fixed end beam, and by analogy with such a beam, moments of opposite sign would be expected at the center and around the edges of the slab. In this case, the idealized collapse mechanism is shown in Figure D. It is useful to have positive yield lines caused by the moments in the middle of the slab, taken as positive by analogy to sagging moments in beams, and negative yield lines caused by the moments around the edges, taken as negative, like hogging moments in beams. In order to carry out the calculation of yield line analysis, it is necessary to know the moment about an axis along a yield line. Consider initially a slab with reinforcement in one direction only. In general, a yield line will be inclined to the reinforcement, as shown in Figure A. It is assumed in yield line theory that the reinforcement bars are yielding, but remain straight, where they cross the yield line. There is enough reinforcement to provide a moment of resistance M per unit width. It might help to visualize the yield line as a series of slips as shown in Figure B. Along AB, the total moment of resistance of the bars crossing the yield line is M times L times sin theta. The moment of resistance per unit width multiplied by the projection of the yield line perpendicular to the direction of the reinforcing bars. The yield of the bars is caused by a moment that acts about an axis perpendicular to the bars. The line with double arrows showing these figures. This moment can be solved into two components, one acting about an axis along the yield line, the other acting about an axis perpendicular to the yield line. These axes are also shown in the figures by lines with double arrows. The component per unit length about the axis along the yield line is denoted by Mn, taking the component about this axis. Of course, there is usually reinforcement in two directions, and the resulting moment about the axis along the yield line can be found from this equation. Figure C shows the most common situation of perpendicular reinforcement. Notice the shorthand in the figure to identify the moment of resistance of each set of reinforcement. The arrows indicate the direction of the reinforcement. Using this equation, we have this expression. The factor mu is used to show that there can be different moments of resistance in the two reinforcement directions. If mu are equal to 1, the reinforcement is called orthotropic. The special case when mu equal to 1 is called isotropic reinforcement. When mu equal to 1, Mn equal to m, so that the moment about the axis along the yield line is the same, whatever the inclination of the yield line. It is worth mentioning the less common case of skew reinforcement, where the reinforcement directions are not perpendicular. A typical arrangement is shown in figure D. Against the using equation of Mn equal to m times sine theta square, we obtain this equation, where alpha is the inclined angle between the two reinforcement directions. Now we know how to calculate the moment about an axis along a yield line. Next, we will use an example to illustrate the application of the yield line method. This example is derived from the model rectangular slab shown in figure A. The large cracks and crushed concrete suggest the yield line pattern in figure B. Tests show that the point of intersection of the positive yield lines, defined by the dimension beta times L, depends on the ratio of the side length and the factor mu that defines the orthotropic reinforcement. Consequently, the actual position of the inclined yield lines is unknown. This means that some complicated expressions would be needed to define the moment about the axis along the yield lines and the rotation of the yield lines. The vector method gives the internal work without too much trouble. Once the work equation has been found, it is necessary to find the critical value of beta. The loading on the slab is assumed to be ultimate dead load Q per unit area, line load Q per unit length along center line. The deformation of the mechanism is defined by the unit deflections shown in figure B. The rigid regions have been subdivided into triangles and rectangles to simplify the calculations. To keep track of the calculations, it is worth numbering each of these. The numbers under each expression correspond to the numbers in figure B. In this way, none of the loading is omitted from the external work. The external work shows here. The internal work needs some thought. Consider the yield lines shown in this figure. Using the vector components in the x direction only, we have the internal work of this part. The same expression holds for the other end of the slab. All the other yield lines are parallel to the x direction and have no vector component in that direction. This means that the total internal work due to x direction components equal to 2 times mu m, 1 at I times alpha over beta. Consider now the part of the slab shown in figure B. The trapezoidal rigid region is flat, so that the angle theta y is the plastic rotation for the y components of every yield line in this figure. We have the internal work of this part. Hence, with a similar expression for the other half of the slab. The total internal work shows here, and the work equation is this expression. This equation relates the moment of resistance M to the loadings Q and capital Q. The critical value of the variable beta is the value that gives the largest value of M for given Q and capital Q, or vice versa. This maximizing process can be achieved by finding the value of beta that satisfies dm over d beta equal to 0, or dq over d beta equal to 0. The second equation assumes that there is some relationship between Q and capital Q. To illustrate what happens, assume that Q equal to 0 to simplify the mathematics. Now we have this equation. Using the quotient rule for differentiation, we obtain this expression, which can be simplified to this quadratic equation. It can be solved to give this beta expression. The only possible value of beta is the positive root. A negative value would indicate yield lines outside the slab. And thus we have this beta critical equation. This can now be substituted back into the 2 times m times 1 plus I equation with capital Q equal to 0 to give the critical solution of the Walker equation. We know beta critical depends on the factors mu and alpha, which define the orthogonal reinforcement and the ratio of the side lengths of the slab. To illustrate the calculations for a real slab, consider a slab 4 meter times 2.5 meter, so that L equal to 4 meter and alpha equal to 0.625. Take mu equal to 0.5 and I equal to 1.5. What M is required to support a factored load of 10 kN per meter square? Using beta critical equation to calculate the value of beta critical, and substituting back in M equation, and we obtain M equal to 1.89 kN per meter width. From conclusions, what we learned? It has examined the yield line method for reinforced concrete slabs. In the yield line method, a collapse mechanism is postulated and analyzed by the virtual work method, or the equilibrium method. It is necessary to determine the critical arrangements of yield lines in a given mechanism, and also to consider alternative mechanisms. Yield line theory can cater for slabs with point loads as well as distributed loading. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,